Yeah, hello. So, just for one more last time, let's see if the audio is better. Right? Could you just confirm it for one more time? Not clear. Still. Let me- Probably this time should work. Is it better right now? Is it better? Okay. Thanks. So, okay, we can start. So, we'll continue our earlier discussion. We were discussing about perturbation theory. So last time around, we looked into some problems on uh, degenerate and non-degenerate perturbation theory. So we looked for some examples like the system when doesn't have any degeneration. So we found out what are the corrections to the wave functions and also energy values like energy eigenvalues. So we have seen the corrections up to first order in energy eigenvalues, if I'm not wrong. So then, uh, then yeah, also same. We found out like how these corrections can be also found in wave functions. But this thing changes a little bit when you have degenerate wave functions. So, for example, some wave function having same energy eigenvalues, there uh, the corrections were quite subtle. It was not very straightforward how we were dealing with non-degenerate eigenstates. So, yeah, so those were some approaches, but there are also some more way to deal with perturbations. So that we will be looking into today's session. So we'll mostly talk about variational principle and WPB method. So I again this would be also uh, already given in your lecture videos. So if you go and check out your NPTEL portal for this registered course, you will at least you would you would found you would find these topics somewhere in week 6 and week 7. So yeah, probably week 7. So yeah, the detailed lectures are there already. So yeah, these are some like typical topics of an advanced quantum mechanics course. So you need to like go through them every now and possible because if you miss any small topic, it will be difficult to carry on. So they are all connected. So just try to be as regular you can. So that you can understand this course much better. So yeah, so we'll talk about variation principle and some related problems. So so Okay. So in variational principle, what you do? So uh, you basically find a upper bound for the ground state energy for any well-defined wave function. So for example, there can be some uh, external perturbation. So by perturbation, like as we have seen from last week, so it is something that external field that is given to your existing quantum system. So on top of your inherent quantum system or inherent quantum Hamiltonian, you have some additional contribution to your Hamiltonian, which is very small. So that smallness is actually allows you to uh, to follow all these methods. So for what we are discussing. So yeah, we will be talking right in this context throughout this perturbation. So where the external field strength is very low. So only then you can able to make all these assumptions or you can apply these methods. So similarly in variational principles, so due to some suppose you have been given some wave function and that wave function captures the uh, the actual Hamilton and also it also has the information of any additional external field if there are any whose I mean strength is very low. Technically, that means it's just a small perturbation is given to your original Hamilton. So, like last time we were talking about some H uh, of your system, which comprises of your natural Hamiltonian, which is something given by H naught, which is the unparted part of your Hamilton, and then there was some epsilon HP is something your uh, part of your Hamilton. So this epsilon has to be very small. So or let's say this is HP. So yeah, fine. So epsilon HP. So this epsilon is basically quantifies the strength of your external photovis, external field or whatever field. So yeah, so last time I think we have seen some examples where you can have some electric field or yeah or some some delta function type. All these things we have seen. So all these are your strength, alpha, QE. They quantifies the external strength, and they are very much less than uh, one, which we have seen. And only then you can able to make all this, do all these approaches. For example, the corrections that we were seeing last time. So it is basically a Taylor series expansion. So Taylor series that you can able to do it if you are like if you are basically like looking uh, into its nearby value. Like when you have a function of x. So if you go slightly away from x, like something delta x, then you can able to do this Taylor series expression, which you can approximate your function. So that is the idea here also. So if you have a small perturbation, then Taylor series expression works for you. Then yeah. So similarly, if for example, if corresponding to this total Hamilton, if some wave function is defined for you, some psi, which basically captures all the information, including the perturbation, then then uh, then if someone asks you what could be the possible value of the ground state energy, so through variational principle, you can uh, at least give a bound. You can give a maximum bound. So this is the maximum bound. Yeah. This basically gives the maximum bound to the ground state energy. So it gives the upper bound for ground state energy for any normalized cell. So I mean, yeah, you can uh, variational. And, uh, Variational you mean basically, uh, like for example, if you, I mean, this approach is inspired from the classical dynamics that we generally solve. So there also, if you have some uh, perturbation, or in general, like if you know about or you're familiar about, like what is variational principle, variational theorems. So where you have something principle of least extent. So it's like I mean, your dynamics always proceeds through in a such a way where your basically action minimizes. So uh, I mean, where your basically your path is minimized. So that idea is something. I mean, similarly, what we try to do here, we see like how this upper bound will be calculated. It's basically evaluating the I mean the we'll calculate this by taking the limit of minimum energy condition. So that is something classically also we do. So and that in that context we have a nice well established uh, I mean complete subject on that, which we call it as variational principle or variational theorem. So yeah, like from there only the idea comes. So it is basically something, yeah, carried. From there. So yeah, it was. Yeah, that is just the name. So that is something borrowed from there, and also like the approach is also something similar. So yeah, so that okay. Thanks. Okay, so uh, now suppose if you have some other let's say some and also what this variation principle, what this statement also tells. Suppose if you have some cipher that let's say that some excited state, some excited state. Then if you take the psi prime, h psi prime, you will get an up and lower bound for first excited state. So yeah, so just like uh, how you have a uh, maximum bound for a ground state energy, similarly you can find a lower bound for first excited state. So yeah, that is right. So when this equality condition can be satisfied in this. statement. So, so this equality condition, like you will find if psi 0, let's say if psi 0 is your ground state, then you will find E, the ground state, is basically your psi 0, H psi 0. So, and if you have any other cell, some linear combination of cell or some, yeah, in that situation, you will find that ground state is always minimum than this ground state will always be less than this right hand side if your psi is some linear combination. So we can see, like for example, we can let's see, find the best out. And E is your E some adjustable parameter. So uh, okay, the first step here is to yeah, the first step is to find out what is your value for your A, because you need a normalized array function. Only then you can prove the statement, prove the statement of variational principle where your ground state dimension should be less than or equal to the expectation of Hamilton for this state. Right. So, so first find out the normalization. So to for a normalized state, you are well aware that psi psi the inner product, or basically in other words is basically uh, the overlap integral is minus the whole space. You take complex value side and multiply its integral has to be 1. So so you just have to calculate this integral, and from there you get what is the value of the. So your psi x is a over x squared, a over x squared plus b squared, so that is x squared. So plus b squared, that is 1. So so you just if you evaluate this integral, so um, I mean So okay, so if you evaluate this integral and calculate what is a, so you'll find 2b2 over 5. So that is the value of a. And so now your size, okay, just one second. Hello. Uh, yeah, sorry for. Okay, so I was talking about, yeah, this normalization factor. Then so yeah, this is basically your wave function. Finally becomes this factor and rest. Now you have to calculate what is your Hamilton, the expectation of Hamilton in this state. So you can write a Hamilton in terms of kinetic and potency. Now you can first you can calculate your first expectation. So that is your first part. So basically expectation of T, the kinetic part. So this is 2b cube over 5 minus infinity to infinity. So uh, so you basically this means you have psi minus h bar square over 2m del square over del x square psi. So this is what you have to evaluate. So otherwise this is written this way. Take the integral from the entire space. So we have psi star and the derivative will be this double derivative, this kinetic energy operator will first operate on psi. So you have to take the double derivative of psi. So yeah, that is 1 over x square plus b square. So so you take first the derivative of 1 over x square plus b square and then again. So it's basically double derivative over then the entire integral. So so okay, so this will give you 2b cube over pi minus h bar square over 2n in integral 0 to infinity 3x squared minus b squared over x squared plus b squared all to the power 4 dx. So now you have to integrate this out. So what you would do is then you have total factor 4 x plus you have 2 over 5 minus h bar square of 2 you have two, two parts in your integral. So first part you have to integrate x squared 2x over square plus b square to the power 4. So first you have to integrate x squared over x squared plus b square to the power 4. And then you have another part. This is minus b square x squared plus b square to the power 4 dx. Okay. So if you let's see. I think there will be also a overall factor of 2 probably. So I have just yeah. Okay, okay, let's see. So yeah, it would be something. You evaluate the integral minus 4 x bar square dq over pi a. So 3 of 3 times 3 pi 16 b square minus uh, then you integrate this that will give you 5 pi over 32 b square. Yeah, so this will come out to be something h bar square minus 4 md square. So likewise, you calculate uh, this part, the expectation of your potential part. So this B is basically uh, so we are talking about harmonic oscillator. So in harmonic oscillator, your V is half mv square. Sorry, it is half m omega square x square. So you have to basically integrate that half m omega square x square in this given reference. So we basically have to calculate half m omega square x x square. Yeah. So half m omega square is your constant. So that is half m omega square. Again, we just have to take the integral. So that will give you 0 to infinity. So yeah, if you evaluate this x square, let me just write down here. So x square is basically 2 times of your 0 to infinity to the 2 power 5 and x square. So basically this 2 comes extra due to because of even function. I'm making this integral 0 to infinity. So using just the identity for even type function, the integral can be reduced to this. So in denominator, you have this x square plus b square whole square. So this is just this integral. So this integral will give you I over 4b to the 2 over 5. Right. So then your v becomes the expectation of your potential is just simply uh, here pi and pi will cancel out, and so 2b will cancel with this 2b in the denominator. So you find your potential expectation of your potential energy will be half m omega square d square. Right. So then you finally found out what is your expectation of Hamilton. So that is expectation of kinetic and potential. So that is x bar square 4 m d square plus half m omega square d square. Now, so here what it was given, uh, you found out what will be your expectation of your Hamiltonian in this given wave function side. Now, if you have an adjustable parameter b, so uh, using this, so this is your varying parameter. So such that there will exist a particular value for b for which your Hamiltonian will be minimized, and that is what basically from this variation principle uh, uh, it says that the minimum bound of your or sorry, the maximum bound of your ground state energy has to be uh, the minimum value of the expectation of Hamiltonian. So so the right. So uh, if you calculate the minimum value of this expectation of Hamiltonian has to be your ground state energy. and anything greater than this will be your excited state, or you can say that this is your lower bound to your first excited state. So your first excited state cannot be less than this. So right, uh, for ground state energy, the expectation of H has to be minimum. So to calculate the, therefore, for a particular value, there exists a minimum of H. So for that, we can compute the turning point by taking the derivative of your expectation of H with respect to B. So uh, this will be zero because that is basically your turning point. Because when you hit a minimum bound, then your behavior of your function changes. So if you consider your this Hamilton function as some function of B, then for a particular value of B, this expectation of Hamilton will be zero. Basically, its derivative will be zero because it hits a minimum bound. That is your minima of your function. That is expectation h. So you calculate the derivative, you will get minus s1 square over 2m d3. So that will be the first derivative. I mean, from your kinetic energy part, from the potential energy part, you will get m omega square b. That is equals to zero. So this will give you, this is b4 equal to x bar square 2m square 2m square. And yeah, b square is basically h bar square root 2 m omega. Yeah, so for this h minimum will be for this value of b. So you have h bar square 4m basically, or maybe I can first write this one with square plus half omega square b square. This will be h bar square over 2m and square root 2m omega over h bar plus half m omega square h bar square root 2 m omega. And this will give you 1 over square root 2 x bar square, x bar omega. So this is like you can think of square root 2 times half h bar omega. And so ideally, for a for an unperturbed harmonic oscillator. For an unperturbed harmonic oscillator, uh, if you take psi 0, if your ground state of Hamilton, then this is what your ground state is. In general, this ground state is half h bar omega, because you know uh, n plus half times h bar omega is your energy eigenvalues for unperturbed uh, harmonic oscillator system. So, but now your psi 0 is not the actual psi 0. That is some different psi, which depends on some variational parameter b. So, upon optimizing that Hamiltonian expectation value with respect to b, you got a minimum value, uh, or rather, it's a maximum value. Uh, yeah. Uh, okay. So where you have uh, in your now your minimum h minimum is square root 2 times the parenthesis naught, means unperturbed limit. So in this case, you have your square root 2 times e naught gs. So this is square root 2 times more than your natural ground state value, that is half h per omega. So uh, okay, so any problem with this, or anything, any issue? Yeah. Yeah. So if there's no problem, we can go to next one. Similarly, let's count the lowest bound energy for a hydrogen atom. Hydrogen atom using the following. You have your wave function. Yeah. So again, you follow this same process how we did before. First, you calculate your normalization. That is normalization factor A. So psi star psi. Now this time you could take over volume because your hydrogen atom is a three-dimensional three-dimensional quantum system. So over volume, your wave function should be normalized. That is a times exponential minus VR square. So that is a square. So we have a all square minus 2VR square. Then can you write your uh, d cube r is your r square sine theta dr d theta d phi. So this is your three-dimensional volume element. This should be equal to this integral should be equal to 1. Now you can split your integrals into respective variables. So first there is integral over r. Then yeah, you have sine theta d theta d phi. Yeah. This integral this depends on angular variables. So this will give you 4 pi. That is pi a square. So only thing you have to solve this integral. Yeah. Similarly, again, we solve this integral. So this is something gamma function type integral. So if you integrate out, it will give you pi over 2b to power 3 by 2 equal to 1. And this is from here you get your a to be 2b over 5 3 by 4. Yeah. Now you got your normalization factor. Now in this normalized wave function, so then your wave function is your 5 to power 3 over 4. So this is your normalized wave function. Now in this normalized wave function, you have to calculate your expectation of H. So again, calculate first T and then potential part. So for yeah, for hydrogen atom system, your your potential is something minus E square by 4 pi epsilon 1 by so say Coulombic potential. So that allows you spherical symmetry in your uh, quantum system, right? Then yeah, you have to now calculate this first kinetic part from here. You get now you can write this kinetic part because you have three-dimensional quantum system. So your kinetic energy operator is basically minus h bar square over 2. Then you have grad square. So instead of this del by del x square, which we wrote down earlier for a one-dimensional system, now you have this del square. So you have to integrate whole full space, full volume. Right. So here you will have this is first square 2b over 5 2 exponential minus b square. To take, yeah. So this is grad square of your r dependent part of your function, and then you have your volume element that is r square into the d r, right? So now for a spherical coordinate system, spherical coordinate system, it's obvious that we are working on a spherical coordinate system. So your del square is basically something written as define this 1 over r square del r r square del r. So this is a del square operator. So when you operate del square exponential of minus b r square, yeah, first you have to take derivative of exponential minus b r square, and then again you have to take derivative with r square. So r square del r. So r square, first derivative will be the minus b plus 2b r. This will be 2 over 2 minus b over square. So, yeah, from here you get minus 2b r square 2r square minus 2b r 4 exponential minus b r square. Right. Then you can use this. Yeah, you use this in your integral. So this will give you minus s square 2b over 5 3 by 2 0 to minus 2b 3r square 2b r 4 exponential minus 2b r square to 4 pi. So this is basically x square over n 4 pi b 2b over 5. So this is again these are your common integrals. 3 over 8b is 3 over 16. So this is an expectation value of the kinetic energy. And then you calculate your expectation of your potential power. This is square over 4 pi epsilon 1 over. So first you calculate the expectation of 1 over r. So you take the volume integral of minus, so volume integral of 1 by that is 0 to then angular part will give you 4 pi. So, so this is something, yeah, your expectation of potential will come out to be something minus e square over 4 pi epsilon naught 2 times square root of 2b over pi. So now you got your expectation of kinetic energy as well as your potential. Now you have your total expectation energy for the Hamilton. So this is h bar square b over 2 minus b square by epsilon twice of square root of 2b over pi. Now again calculate the minimum energy. So here also the varying parameter is b. So right. So here also your varying parameter is b. So just like how we varied b, basically for a given value of b, your this expectation energy will be minimum, which is basically your ground state energy. So if you take the so you calculate the derivative and equal to with zero, that is 3h bar square over 2n from first term, this derivative is going to 5 epsilon naught 2 pi derivative 1 over 2 2 2 p. So that is 2 equals to 0. So from here you get your p equals to 2 square 3 square square e square over 5 square and it's over 5. Okay. Yeah, so now you use this your beam in your explain. So that will give you 8 by 3 pi. Then you have minus n over 2 h bar square e square by 4 pi epsilon square square. Now this is your natural ground state energy of the hydrogen. So now you are getting 8 by 3 pi times Yeah, 8535 times V1. Okay. Is there any doubt or any problem? Anything you missed out or something not clear? Any issue? Any, uh, do you have any doubt? If you have any question, then please you can unmute and ask. Okay. Any question or you can unmute or ask. Then if any problem or yeah, is it clear for you or not? Like I think you were asking, you were getting some doubt, right? Phone. Okay. Yeah. So that is how you get this minimum bound or the bound for your given uh, quantum system to be. Uh, I mean, it's basically you have a variational parameter. If you optimize that parameter, then that parameter has particular value. And if you tune that parameter exactly that, uh, then you will find your that quantum system corresponding to that value of your variational parameter, whose wave function will be some particular wave function, and in that particular wave function, your ground state is minimum. So that is what you have to calculate. And right. So any energy value greater than this h mean will basically give you the first excited state, or it can give any other excited state. So next we can discuss something about WKT. So again, this is something that has been discussed very well in your uh, lectures. If you go through them, you will find there will be very, detailed and extensive discussion has been done. So this WKB, this acronym is something named by these three potential frames below. So what it is in this so uh, basically you want to understand how a function would behave at the uh, semi-classical limit. And basically, when you take h bar to zero, then uh, I mean, like how you can approximate your wave functions and yeah, and other like energies and how. So I can give you a very brief overview of how uh, this this is something studied. So let's consider there are some uh, like subtle features upon which you define this method. So where your I mean your potential should be slowly varying and so on. So that what we can see. So let's start. Suppose you have a low varying one dimensional potential V of x. Your V of x is something to x. Yeah, something of this form. And these are your some turning points. X, E, and so, so you can write your Schrodinger equation time independent. Yeah, so far what we have discussed all these methods from last time around, like all the problems that we have been solving, considering everything that your Hamiltonian is time independent. So once you have time dependent, all these methods will simply will not work. Drawing the equation is right minus h bar to 2 square sine x inside. So for a uniform potential V, you can write psi s exponential high k. But suppose, as we are telling, we are having a smoothly, we are having a slowly varying potential, then you can uh, uh, parameterize your wave function, or rather, you can basically you write the same wave function in the following. So let's say for a smooth potential, by that it means it's a continuous, well-behaved potential function. So then wave function in that case psi of x exponential I sigma of x, where sigma is any complex. Yeah, it's a complex function. Now, to if you substitute this in Schrodinger equation, so let's call this as a system. So we in a video. Yeah, right. So you can write down. So from this first term, we basically have I sigma over h prime, I h prime, and sigma h minus I sigma by del x. Yeah, and then rest you have yeah yeah you can finally write this in this form where your Schrodinger equation can be written down as L square sigma over del x square. Yeah, okay. So this is equals to uh, e square x or your e of x is basically 2m e minus v of x and whole square. So this is basically your momentum. This is defined as h over lambda. Right. So this is how for a time varying potential you can write down or basically your slowly varying potential you can write down this Schrodinger equation where your sigma is basically um, uh, like for a constant potential you have your wave function something of this form uh, exponential ikx, but when your potential is something slowly varying in x, then you can write your k as something sigma of x. So then your wave function is something defined to be this. Then correspondingly, you can get a Schrodinger equation of this form, where uh, p, uh, which is also changing with x slowly, where it is also slowly varying since yeah, because you are defining in terms of v of x, and this is also equal to x by lambda. So so it's basically your p is something related with momentum, or that is the k, the wave number that we usually define. Okay. Uh, Now you can the solution to find solution for the given form of Schrodinger equation. You can write, you can we can expand sigma of x as power series in h bar. So that is you can write sigma as something sigma naught for h bar I, sigma 1 as h bar over I square, sigma 2 plus. So this is something you think of as your answer. And if you put this in your equation, so this is C, and this is your D. Now, if you comparing the h bar to the power 0, h bar square, and so on. So first using equation D in C, then we can write down del sigma 0 or del x whole square is basically equal to yeah, this is equal to p square x. This means your sigma 0 is basically equal to plus minus p of x dx. So I'm comparing only power of h bar to the 0 and h bar to the power 0 order 0th order basically. So here, what we find here, I mean, you can write this term. Okay, this is true only h bar del square sigma del x square and del sigma over del x. So this is where the modulus should be, or otherwise dot and sigma variables. This will be less than 1. This is the approximation we have to look at. So this is basically or otherwise you can also say this is 1 over 2 pi then then lambda of x by x is less than if del sigma by del x is your q of x leading approximation and p of x is your 2 pi h bar over lambda of x. So that is what we mean here, that wavelength which is changing over distance should be very small. In that situation, you can consider your wave function, which we define as something uh, psi of psi equals to exponential I sigma of x over h bar. And sigma, you can write it as something of this form. So this is your uh, WKV approximation. So then we also have to find out what are sigma 1, sigma 2. The sigma 0, we find out sigma 0, you can write it down as this. Then what could be sigma 1 and sigma rest? Basically, uh, then here we look for the order of x0. Similarly, if you look for order of x to the power 1, then you have something this. That is more. So, first to determine sigma 1, uh, again, uh, we used equation T in C to find out what is sigma 0 by comparing the orders of h bar by comparing the zeroth power of h bar. So from there we find out something sigma zero is p of x dx integral. And similarly for sigma 1, uh, we will get something. We simply again using equation b and c, you will find out uh, minus I h bar n squared sigma 0 over lx squared plus del sigma over del x squared equals to e square of x. Yeah. Then using del sigma 0 over del x, it's p, what we get. So this will be del x del sigma 1 over del x equal to del square sigma 1 del x squared by 2 itself del sigma 0 over del x. So this is minus 1 by 2p then p by del x. Otherwise, sigma 1 of x we can write as minus half log p of x. So this becomes exponential of sigma 1x is 1 over square root 2 p of x. So up to order of x bar, we can write our wave function psi of x as uh, c1 p of x. So we find out what is sigma naught sigma 1. So using that, what we can write down. So first we assume our wave function to be this v. So this was our equation b, and there was equation b using this two we can write. So we found out what is sigma 1, that is this is sigma 1, and also sigma 0. Right. So using sigma 0 and sigma 1, we can write the wave function as this integral u dx. Uh, in general, it will have two components, plus and minus. So we are giving for plus as C1. So there will be another, let's say C2 over same, but this will be minus I1 h bar. PDX. Yeah, this minus something psi is C1 matrix plus C2 minus I. Okay. So just you have to use this entire sigma 0 into this sigma x. Like sigma 0 and sigma 1 will find out just here. So that is what psi is. But again, this is not the full thing. We have to also understand what happens at the uh, classically forbidden region. So you will find as classically forbidden region, this momentum goes to zero. There was one relation where yeah, this momentum goes to zero. That means this lambda is infinite. So this is, and this will like your spoil your wave function. I mean your wave function doesn't go, or it basically it will diverge. So I mean these are not well defined wave function at the turning point. So how to deal with that? There are uh, so let's say your potential, as we discussed at the beginning, something. Yeah, this is your turning point and the other turning point, not the turning point. Basically, your uh, this is your boundary. You have two boundaries for a given value of quantum particle that has energy zero. So this is energy. So classically, your quantum particle should be restricted between this A to B. Cannot go over A. For a particle having energy, this energy is zero corresponding to this. So what happens then? Uh, so for your now we have to find out the wave functions at every region for x greater than a, much greater than. So for x greater than, you can write your wave function as limit s greater than a. Your psi x should be c over inverse of x exponential minus 1 over x bar a to x e dx. So this piece should be and for reason b unit with this limit. So this means close to region A, around this region or this region, this region. So somewhere close to A, but not A greater than X. So not x greater than n, but uh, x less than n, but close to a, not near b. And it's far away from b. So let's say your particle is somewhere here. So what would be the reference? Then the reference is something given as co dx. This is cos of pi over 4 minus 1 over extra x 2 dx. Yeah, and similarly, uh, this is, let's say, first uh, classical turning point for second classical turning point. This is x equals to a, and this is x equals to b. So here, the limit is to b is less than x, but, but your x is very much less than a, far away from it. So this is like this. You need to have a function is basically c prime cos over x bar v2 x v dx x by the. Now within this region, within this region, I mean your wave function should be one because this is one defined region. But you see, uh, I mean we are using two different constants c and c prime. So that should be equal. Other than the some phase vector. Phase vector can be different in both this part because if your particle is somewhere here, it would be having some other phase. It would be here some. It can have some other. So for c prime equal to c, then uh, it implies that the difference of this phase, this this should be e2 x p dx minus pi by 4 pi by 4 minus 1 over x bar x2 p dx equal to n pi. And now this gives a familiar relation. This is complete or complete path to date from uh, a to x and x to b, or b to x or then x to a. Then this is complete contour. This is our complete loop. This PDX is basically 2 pi h bar n plus half. So this gives you Bohr Sommerfeld contradiction. Okay, so these are the things like I'm just giving you some overview of all this. I mean, the form of wave functions and I mean in this WKB method. So these are very explained in detailed way. You can check out lectures. But here I will show you one example. Let's say uh, in quantum harmonic oscillator. So what some of the quantization what some of the so estimate wave functions by WKB approximation. So now you know in harmonic oscillator we have the maintenance. Now this P of x, if it is said that it is slowly varying, then we can use WKB approximation. So this is given in your question that your V of x is slowly varying. Let's see where V of x is slowly varying. Then show the proportional quantization. So for the you write your P of x, uh, you can this P of x initially we wrote this thing. So using this P of x, you can write P minus your P of x is numeric square extra over 2. This is your P of x. Then at classical turning point, your P of x is 0. So this means your E is equals to half L omega square. That's your turning point is x naught. Then you have two turning points, one at plus 2e over m omega square and other negative 2e m omega square. So we find out the turning points. So then away from turning point, your wave function uh, let's say now let's call this as yeah. Now using this wave functions, we can write down your wave function for a harmonic oscillator whose potential is slowly varying. So for uh, x great, uh, less than x0, you can write psi of x is C1 to Px, then cos of pi by 4 minus 1 over h bar x2 x naught p dx. Right. So this is your, yeah, for x less than x naught, for x greater than x naught, your psi of x c by twice of px exponential minus 1 by x bar x0 to x p dx. So we have used this to relation. So this is for x greater than x naught, which we know, and this is for x less than x naught. So in harmonic oscillator also, you can think of your potential something this. This is your x, this is v of x. Suppose the particle has energy E, and this is your x naught, and this is your minus x naught. So we have written down your function in this position. Let's say the particle is somewhere here, and your particle is somewhere here. So, so this is for x less than 0 and x is greater than 0. Right. Then yeah, there was also something which we can show the most of the quantization and quantum harmonic oscillator. So that is what I think we let. Let me complete this wave function part. Then what else you have? Uh, 1 second. Yeah. So there was Yeah, for quantization group, so this is how you can write down your weight function for WT. So same you can write down around I mean for this turning point as well, which is negative of x here. But now uh, for so about quantization to harmonic oscillator, what you can do, you can write down the board quantization group, p of x dx should be something uh, n by it should be something 2 by h bar times n plus r. This is what we found out. So now we have to see whether quantum harmonic oscillator what you are getting. So your p of x as we defined before. So this p of x is this. So 2 e minus and omega square x square over 2. This is square root, and your integral is over complete loop. So this I can write it as, because since you have a symmetric potential, whatever you have from 0 to x naught, the same you have from minus x naught to 0. So I can write it as twice of uh, minus x naught to x naught. Uh, right. Then this is our complete periodic cycle. So suppose if your particle goes starts from minus x naught, then it should come back to minus x naught. So in a harmonic oscillator, your uh, yeah, I mean over one period you have two symmetric half cycles. So this is now you can write it down as uh, this is so this is ultimately proving something 2 by e by omega. Like how I am saying this, because your uh, from both symmetric quantization we found out that your this xn, this basically this is your xn, it is quantized. uh, you can see it depends on some quantum number, and so this is equal to 2 by h bar n plus r. Then we know in quantum harmonic oscillator your energy is something given as n plus half h bar omega. So using that, I can write this is equal to something 2 pi of e by omega, because if I use this over here, this can give me 2 pi h bar n plus half. So maybe we can discuss more on this, how we can derive this maybe in the next class. But since we um, we're we are almost up to the time right now. So, but this is how you can see that the this uh, action for this quantum harmonic oscillator, this will be something has to be equal to uh, 2 pi e over omega, because e we know in quantum harmonic oscillator is given as n plus half h bar omega. So yeah, this later topics, as I said at the beginning, these are some really typical topics in your advanced quantum mechanics, which I mean, you need to go through very carefully. You should not miss out any single small topic even. So they are all connected and much important if you are looking to do physics in future. This is something very useful. And also, there are other topics which you have seen already, like related to quantum information and some more, where that could be useful in other areas like quantum computing. If you wish to do some 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 profession or some um, or also some sort of research that could be very useful, because quantum computing is something very uh, like I mean, a very demanding topic at the time. So, quantum computing, whether in the area of engineering or in industry or even in research, is very important. So, that is one topic that quantum information would be useful to you. And these are other rest other topics where we have seen perturbations and before that you have seen uh, like quantum particles and some extra field like magnetic field that get based to many other effects like magnetic resonances and all those. So they are and they are very important in other aspects. So yeah, so advanced power mechanics like this is really giving you a big chance to explore yourself to some modern research problems where you can directly use whatever you are learning here. And, yeah, so that was for today's topic. And I know this is something very rigorous, but uh, anything that you missed out anywhere in this discussion, please let me know. If we can discuss again in the next week, or also if you can communicate through the forum also. So yeah, uh, that is for next session. We will meet again. Yeah, then this was our we, yeah, we will have two more sessions. One will be your penultimate session, that is will be and that will be on next week. Your BTEC, your last week, but then there will be one more additional week, which will follow soon after that. So yeah, then until then, uh, those two sessions are of course eligible your test, which you will be appearing for your course for this course very soon. So again, something related to assignments or some problems you are still facing issue, then please let me know. We can try to solve this night and next. So yeah, and, yeah, that is for this session. Let's see you.